Welcome to this explainer. Today, we're rolling up our sleeves and doing a highly technical autopsy on CVE 2026-4670. This is a critical vulnerability found in Progress MOVEit Automation, and we're going to look at exactly how a seemingly simple logic flaw in a backend service can instantly spiral into a massive enterprise risk management crisis. So, whether you're a software developer writing the code, a security engineer defending the perimeter, or even if you're trying to figure out how to explain business continuity risks to non-technical leadership, you're going to find this case study incredibly revealing. Let's get right into it. Here is our roadmap for today. We'll quickly cover the overview and original intent, abstract the vulnerability, trace the attack flow and root cause, look at the impact, discuss the patch, and wrap up with some key secure coding lessons. All right, Section 1, Overview and Intent. Let's set the stage. A CVSS score of 9.8? Wow. You really don't see that every day, right? That is a massive, critical severity score, and it's absolutely justified here. What we're dealing with is an authentication bypass that completely circumvents login requirements. In plain language, a remote, unauthenticated attacker can exploit this over the network with literally zero user interaction. They don't need to steal passwords, they don't need phishing emails, they just need access to the right network port. Now, to really grasp the risk, we have to understand what the software actually does. You probably remember the massive 2023 ransomware headlines involving MOVEit Transfer, right? Well, Transfer is the product that stores the files. MOVEit Automation is different. It's the centralized intelligence engine. It's the brain that securely schedules and moves highly sensitive data, stuff like payroll and financial records, between completely different systems. It's the core of an organization's data workflow. So, where did things go wrong? It boils down to a classic mismatch between a developer's expectation and the messy reality of enterprise networks. The developers designed the service backend command port, which is usually port 3474, kind of like an employee-only door. They just assumed the network would isolate it, meaning it would only ever receive commands from trusted administrative clients or local processes. But the reality? In actual enterprise deployments, these backend interfaces get exposed all the time, sometimes broadly across internal networks, or, horrifyingly, straight to the open internet. Moving on to Section 2, Vulnerability Abstraction. How exactly does a bad network assumption turn into a critical vulnerability? Well, what's fascinating here is that this isn't your typical memory corruption issue. We aren't looking at some complex buffer overflow where an attacker is forcing malicious code into memory. No, this is classified as CWE 305, Authentication Bypass of Primary Weakness. It's a fundamental failure in the application's gatekeeper logic. The authentication algorithm itself might actually be perfectly fine, but a completely separate implementation flaw lets an attacker send a specific input pattern that tricks the system's state machine. It basically tricks the system into saying, yep, this user has already passed security. Come on in. Okay, Section 3, Attack Flow and Root Cause. Let's pop the hood. To really understand the business continuity risk here, we have to dissect how an attacker actually pulls this off. It's shockingly simple. First, reconnaissance. They scan for an exposed port 3474. Then, initiation. The attacker sends a specially crafted network request. Because of that primary weakness we just talked about, the backend processes the request and completely fails to verify if the requester is actually trusted. And then, the bypass. The system incorrectly initializes an administrative session. Just like that, boom. Without typing a single credential, the attacker has full administrative control, meaning immediate access to the task library and all those juicy remote server credentials stored inside it. So what does this look like at the code level? The root cause is a total, fundamental absence of interface-level authentication. The backend basically looks at a specific command type or header flag, and without cryptographically verifying a session token, it just blindly accepts it. It totally fails to validate administrative trust boundaries. The application looks at the structure of an incoming command, assumes it's an internal trusted process, and executes it. For any developers listening, this is exactly why secure coding patterns dictate that you can never implicitly trust an interface.
Let's move to Section 4, Impact and Scope.
Now, this is the part you really need to translate for your non-technical leadership because a technical failure here instantly cascades into a massive data governance nightmare.
The impact is staggering. The attacker effectively becomes the global administrator. They now hold the SSH keys and passwords to your organization's most protected assets. They can tweak workflows to create a malicious hop, meaning they can silently copy every sensitive file to their own external servers before the data even reaches its intended destination. Or they can execute system commands to deploy ransomware, or even chain this with CVE 2026-5174 for privilege escalation. This is a worst-case scenario for business continuity, and it is highly reminiscent of those devastating Clop ransomware campaigns. The scope of this is incredibly vast. All versions prior to 2024.0.0, as well as the specific version branches you see detailed here, up to 2025.1.4, are completely vulnerable. And to put the scale of this into perspective, security researchers noted that over 1,400 instances were exposed directly to the open internet at the time of discovery. That is a massive attack surface. Please take a second to cross-reference your own environment with this vulnerable scope. If you're running one of these, you need to take action right now. Which brings us to Section 5, Fix and Mitigations.
So how did Progress Software actually fix this? The patch works because it goes in and fundamentally hardens that backend command ports filter. It shifts the application logic into a strict default deny state, and it introduces a mandatory identity verification step. This means absolutely no request, no matter how convincing the header structure looks, can bypass formal credential checks. Now, if for some reason you literally cannot apply the patch today, your only viable mitigation is intense network segmentation. You absolutely must restrict port 3474 access strictly to highly trusted administrative IPs.
I also want to give a quick shout out because this critical flaw was discovered by a brilliant team of researchers over at Airbus SecLab. This discovery is a perfect example of the immense value of bug bounty programs and the power of advanced fuzzing techniques. It proves without a shadow of a doubt that just because an interface is undocumented or just because we consider it internal, it is never immune to rigorous security research or to threat actors looking for a way in.
Let's wrap things up with Section 6, Key Lessons. What are the actionable secure coding patterns you need to take away from this? For developers, eliminate implicit trust. Never ever assume an interface is safe just because it sits on a backend port. You have to validate administrative trust boundaries strictly. Require secure session tokens for every single transaction. And for the security teams out there, your job is to aggressively monitor audit logs for anomalous backend activity. But more importantly, you have to translate this technical risk into language your leadership understands. A compromised task library isn't just an IT hiccup, it's a catastrophic failure in data governance. I love this quote because it perfectly summarizes the paradigm shift we need right now. Developers should always implement a zero-trust model at the interface level. We have to move away from perimeter-only thinking. Authentication bypasses like this happen the exact second we assume a network boundary is a valid substitute for code-level authorization. And that leads us to our final thought. Thank you so much for joining me for this explainer. I want you to take a hard look at your own architecture today and ask yourself this one question. If your network perimeter failed right now, would your internal backend services blindly trust the attacker? Make sure your internal trust boundaries are truly secure. Stay safe out there, and I'll see you in the next one.